Okay.
So, Manizheh, can you hear me? And am I pronouncing your name correctly?
Yes.
I'm sorry that your second name probably will defeat me, but I would like to attempt to introduce you. First, I should say we're very pleased and honored that you are able to present your work to us today in this seminar series. And I apologize that we had to make a change of the day. I hope it wasn't too inconvenient for you. I don't have a great deal to say except that you're talking to us from Iran, where you work at the University of Kashan. Is that correct?
Yes.
And the title of your talk, which is close to the interests of many of us here, is Induced Energy Momentum Tensor of a Dirac Field in Two-Dimensional de Sitter Quantum Electrodynamics. So I'd like to hand over to you if you could share your screen. But Manizheh, do spend a few minutes telling us about yourself and about your interests before you tell us about your work, because I think we'd like to know a bit more about you.
And sorry, and I think so the speaker would prefer that we ask questions after the talk. So it would be good if we can ask questions in Q&A sessions. Please go ahead, Hania.
First off, I should appreciate Professor Davis, who has given me this chance to have a presentation about my work. Besides, I should thank Dr. Helling for making it possible to me to have this lecture. I will be talking about a brief introduction of my work. According to inflation hypothesis, which predict the typology of space-time in the early universe, is similar to de Sitter space-time. The study of Schwinger effect and its properties in de Sitter space-time is of interest to researchers. The existing of a strong electromagnetic field in the early universe and their effect on the creation of pairs have made it important to study the Schwinger effect in this field of research. Thus, this effect has been investigated in various dimensions of de Sitter space-time for scale particles and fermion particles. This is the first time that issue of regularized energy momentum tensor has been investigated for fermion field in de Sitter space-time. Although field theory in curved space-time has been studied for many years. In the curved space-time, for fermion field, due to interaction the SP with the gravitational field background, the computational complexity is higher than the scalar field, which has zero SP, so that it had less studied so far. The importance of calculating and studying the energy momentum tensor is that this quantity is the source of gravity in Einstein field equation. In cosmological and astrophysical application, the energy momentum tensor is used to study the back reaction effect of pair production in gravitational field. According to the inflation hypothesis, space-time in the early universe is similar to de Sitter space-time that has maximal symmetry. On the other hand, due to existing of a strong electromagnetic field in the early universe and their effect on pair production, I have focused my research on the Sitter spacetime. To understand this phenomenon, one of the most important concepts is to study the properties of energy momentum tensor. Cosmological application motivates me to compute the energy momentum tensor of the created fermion particles in the Sitter spacetime. The theory of regularization for quantum electrodynamics in Minkowski spacetime has been well studied. In curved spacetime, especially in the Sitter spacetime, there is no unique vacuum that can be used to calculate the expectation value of physical quantities. Gravitational interaction, which do not exist in flat spacetime, also added the complexity of regularization theory in curved spacetime. Perhaps one of the most efficient methods to regularization expectation value of quantities is the adiabatic subtraction method. This method is based on approximation that creation of a particle with frequency much larger than energy scale determined by curvature of spacetime can be neglected. Hence, the adiabatic expansion is a cover series of spacetime curvature. Especially in the case of Friedmann-Lemaitre-Robertson-Walker spacetime with a spatially flat metric, the number time derivative of a scale factor determines the adiabatic order. With the use of covariant point splitting regularization method, finite energy momentum tensor for a scalar field has been calculated by Professor Davis and her colleagues in spatially Friedmann-Lemaitre-Robertson-Walker spacetime and the Sitter spacetime, which is in agreement with the results obtained by applying dimensional regularization technique. It was proven that the adiabatic and point splitting regularization methods are equivalent in Friedmann-Lemaitre-Robertson-Walker spacetime. The method of dimensional regularization is restricted to only a spatial spacetime, which can be generalized to n-complex dimensions, and associated field equation can be solved explicitly. Although the point splitting method can be applied to any spacetime, it deals with the difficult calculation for simple case of Friedmann-Lemaitre-Robertson-Walker spacetime. It is emphasized the method of adiabatic regularization, which deals with mode-by-mode subtraction process, is especially convenient for problems in which numerical calculation must be performed. Hence, from a cosmological point of view, which necessitates to use of numerical method, adiabatic regularization is desirable. This fact illustrates the importance of adiabatic regularization method and motivates me to consider this method in this work. In this work, I consider a massive Dirac field coupled to a uniform electric field which constant energy density on the Poincaré patch of two-dimensional de Sitter spacetime. I assume the electric and gravitational field as classical I assume the electric and gravitational field as classical background, which are not affected by the presence of Dirac field. The half of two-dimensional de Sitter spacetime can be represented in a spatially flat Friedmann-Lemaitre-Robertson-Walker spacetime, where T is a proper time and H is Hubble constant. By using transformation of equation 2, the metric one can be expressed in a manifestly conformally flat form. In order to have a uniform electric field with constant energy density in metric 3, I choose the electromagnetic vector potential to be, where E is a constant. The quantum electrodynamic action for Dirac field psi of x with mass m and charge E, which is coupled to an electromagnetic vector potential 4 in two-dimensional de Sitter spacetime with metric 3, can be written as, where G is a determinant of metric and gamma mu are Dirac gamma matrices in two-dimensional de Sitter spacetime. I also introduced the tetrad field with the help of two-dimensional Minkowski spacetime. I choose the tetrad in the gauge of equation 7, then the Dirac gamma matrices in the Weil representation are given by equation 8, where sigma 1, sigma 2, and sigma 3 are Paul matrices. In this representation, the adjoint Dirac field psi bar of x can be expressed as equation 9. The gauge covariant derivative can be expressed as equation 10, where the spin connection B mu is given by, where I use the over dot to denote the derivative with respect to conformal time. The Dirac equation follows from action 5 given by equation 12. By using the fact that the Dirac equation 12 is invariant under a spatial translation, I can write psi of x as decomposed to component mod spinor as equation 13. Substituting the decomposed form of spinor 13 into Dirac equation 12, and by using equation 4 and 8, I arrive at a system of coupled differential equation, where I have defined adjoint momentum as equation 15. The system of coupled first-order linear equation 14 can be converted a single second differential linear can be converted to a single second order linear differential equation of equation 16, where where conformal time dependent frequency is given by the solution of Dirac equations 16 with desired asymptotic behavior at the early time to approach minus infinity and late time to approach zero, which describe the in and out vacuum state respectively, have been obtained in reference 1. I want to compute the expectation value of energy momentum tensor in Hadamard in vacuum state. Therefore, I take only solution of Dirac equation 16 with desired asymptotic behavior at the early time. Hence, the component of normalized positive frequency mode spinor are given in reference 1, and component of normalized mode spinor and the component of normalized negative frequency mode spinor are given by equation 12 and 20 and 21. Where W is Whittaker function, and I have the normalized state function has been defined as, I have defined the dimension variable as to normalize the mode spinor component, which are given by equation 18 to 21, may be represented in doublet form as equation 24. Then it can be shown that these doublets satisfy the relation where doublet struct denotes 2 by 2 identity matrix. The set of complete orthonormal mode spinor 24 determine the in vacuum state, which is annihilated by acting operator AK for Fermion and BK for anti-Fermion. Then the focus space of a state vector can is built by successive acting decreation operator IK dagger and BK dagger for Fermion and anti-Fermion. To quantize the Dirac field psi of x, I impose the anti-commutation relation as equation 27. Then the quantized Dirac field operator psi of x can be written as equation 28. The energy momentum tensor of Dirac field is defined by variation of metric with respect to variation of inverse metric. After some algebraic calculation, the definition 29 yields the expression for energy momentum tensor of Dirac field coupled to a uniform electric field background in two-dimensional de Sitter spacetime. By considering the Dirac field psi of x as quantum operator and relation 26 and 27, I arrive the following expression for the in vacuum state expectation value of energy momentum tensor. The timeline component is given by where R denotes the real part of expression, P P is dimensionless physical momentum, and lambda is cutoff. For the space-like component I have, and the symmetric of diagonal component obtained. To regularize the ultraviolet divergence in the momentum integral, I have considered cutoff lambda equal minus K2. To evaluate the integral over momentum involving the Whittaker function, I follow the procedure that introduced in the reference 3 and 4 for computing the induced current for a scalar field in DS2 and DS4. This method has been used by using this method, the induced current for Dirac field in DS2 in reference 1 and DS4 in reference 2 has been computed. The appropriate Milling-Behrens integral representation of Whittaker function is given by which is valid for arbitrary value of the phase of argument in the domain. The condition is that the contour of integration must be arranged in a way that change of poles gamma of 1/2 plus gamma plus s times gamma of 1/2 minus gamma plus s lies apart from change of poles gamma of minus k minus s. Then I obtain the finite result for time-like component and for a space-like component, where log denotes the natural logarithm function, and the gamma psi is defined by first variation of logarithm gamma function. To remove the ultraviolet divergence from the expectation value, I apply the adiabatic subtraction scale. In the adiabatic regularization method, we assume that when the energy of a single particle is larger than energy scale of curvature spacetime, the production of single particles can be neglected. This means that the number of particles in single mode should not change if the change rate of a scale factor is slow or adiabatic. Thus, the adiabatic order is equal the number of derivatives appearing in an expression. This method has been used to regularize the induced fermion current in DS2 in reference 1 and DS4 in reference 2. As usual in literature, I assume the electromagnetic vector potential and energy momentum tensor is the in two-dimensional de Sitter spacetime to be of adiabatic order 0 and 2 respectively. I begin by considering WKB type solution for Dirac equation as where A equal 1 and 2 is the spinor index and NA is normalization coefficient. And real function XA and YA are required to satisfy the equation 38 and 39. Inserting function YA into mod spinor 37, I find the UA can be expressed as equation 14. Then substituting the equation 14 into coupled Dirac equation yields an algebraic equation for function XA, which exactly as the remaining undeterminate factor in mod spinor 37 is normalization constant. The ratio of counterter is independent of NA. I cancel the component of adiabatic mod spinor 37 to obey the normalization condition of equation 42. Following the adiabatic regularization method, the set of counterter are constructed from expectation value of the energy momentum tensor component 13 in the adiabatic vacuum state, which described by solution 37. Such expression can be written as equation 43 and 44, where K is an ultraviolet momentum cutoff, and of diagonal component momentum is given by equation 45. By defining the ratio of spinor components, I can rewrite the equation 43 and 44 as equation 47 and 48. Substituting this expression in coupled Dirac equation, I obtain equation 49. That ratio of counterter is dependent of normalization constant. I now return to equation 41 I return to equation 41 to find the solution for function x1. Obviously, term appearing on the right hand, on the right side of equation 49 are of two higher adiabatic order than those on the left side. By using the fact that conformal time-dependent frequency is of 0 adiabatic order, at the lowest adiabatic order, function XA is obtained by equation 15. Then up to second order adiabatic expansion of XA is constructed iteratively and is given by equation 51. Hence, the adiabatic expectation x1 up to 0 and 2 are read from equation 15 and 51, then substituting the second adiabatic expression of the right-hand side of equation 49 into equation 47 and 48, we arrive the equation 15.2 and 53. Then subtracting the second adiabatic order counter term of original expression for in vacuum expectation value leads to the regularized energy momentum tensor for a space-like component and time-like component. The important result is that the off-diagonal component of regularized induced energy momentum tensor vanish. Therefore, I examine the regularized energy momentum tensor T00 and T11. In figure 1 and figure 2, I have logarithmically plotted absolute value of T00 and T11 as function of parameters electric field lambda and Dirac field mass. I should be noted that in figures 1 and 2, the points at which T00 and T11 became 0 appears as sharp singularity in the logarithm plot of the absolute value of this expression. Thus, the component of induced energy momentum tensor are analytic and continuous function of parameter lambda and mu. The magnitude of diagonal component of induced energy momentum tensor increase as Dirac field, as electric field increase and decrease, and as mass Dirac field increase. Expect in the very near vicinity of their 0 point. I now analyze the induced energy momentum tensor in the limiting value of Dirac electric field and Dirac field mass to find the explicit asymptotic behavior shown in figures 1 and 2. In the strong electromagnetic field regime, the asymptotic behavior of induced energy momentum tensor is obtained by expanding T00 and T11 in a Taylor series about lambda equal infinity with constant value of mu. I then obtain the leading order term as equation 57 and 58, which is constant with the behavior of energy momentum tensor shown in figures 1 in this domain. In the weak electric field regime, the asymptotic behavior of induced energy momentum tensor is obtained by expanding T00 and T11 in a Taylor series about lambda equals 0. For the case of light Dirac field, I obtain the leading order term as where gamma E is Euler constant. And for the case of heavy Dirac field, mu is a lot bigger than 1. The leading order term are given by equation 62 and 63. For the case of heavy Dirac field, I expand T00 and T11 in a Taylor series about lambda mu equal infinity with constant value of lambda. I find the expression as equation 62 and 63 will approximate the behavior of diagonal component of induced energy momentum tensor as long as lambda is a lot smaller than mu. The trace of induced energy momentum tensor reads from equation T00 and T11. The absolute value has been logarithmically plotted in figure 3. For the constant value of mu, as lambda increases from 0, t goes to large negative value. Thus, as shown in figure 3, its absolute value is an increased function of lambda. In this case, at the point lambda equal lambda star, at which t became 0, a sharp singular behavior appears in the logarithm plot of the absolute value of t. Hence, the trace of the induced energy momentum tensor is an analytic and continuous function of parameter lambda and mu, whose magnitude increase as electric field increase and decrease as mass increase, except in the very near vicinity of its 0 point. I emphasize for the case of light Dirac field, the trace is negative. For the case of heavy Dirac field, the precise value of lambda star is evaluated by solving the equation T of mu and lambda star equals 0. For the case of, for the lambda is smaller than lambda star, the trace is positive, and for the lambda is larger than lambda star, the trace is negative. To find the behavior of Dirac field mass, to find the behavior of lambda star against the Dirac field mass parameter mu, I present figure 4, shown as lambda increase as mu increase. I point out some consequence of trace of induced energy momentum tensor, trace anomaly, and gravitational field background. The trace anomaly of induced energy momentum tensor is derived by taking the limit of lambda approach 0 and mu approach 0 in expressions 16.4, which yields t equal minus r over 24p, where r equal to h squared is Ricci scalar curvature of two-dimensional de Sitter spacetime. This result agreed precisely with the well-known trace anomaly reference 6 of Dirac field in two-dimensional de Sitter spacetime. Gravitational back reaction. In reference 7, the back reaction effect of induced Dirac field, the induced Dirac field current on the electromagnetic field background in two-dimensional de Sitter spacetime has been studied. The main conclusion was that the back reaction of fermion pairs does not amplify the electric field background. I want to study the back reaction of induced energy momentum tensor on the gravitational field background. A natural way to do this is to use of Einstein field equation. However, as is well known, there is no Einstein gravity in two-dimensional de Sitter two-dimensional space-time. Perhaps one of the most natural analog of Einstein gravitational field equation in two-dimensional is given by equation 67, where R is a Ricci scalar and lambda is cosmological constant and G is Newton's gravitational constant in two dimension, and T is a trace of energy momentum tensor. In two-dimensional de Sitter space-time, the cosmological constant vanish. Hence, we set lambda equals 0 into equation 67. In natural units, Newton gravitational constant G should be dimensionless in two-dimensional space-time. Hence, in two-dimensional de Sitter space-time, the Newton's gravitational constant in terms of Planck mass and Hubble constant can be written naturally as G equal h squared over mp squared. To explore the consequence of induced energy momentum tensor, it is convenient to define the time-dependent Hubble parameter as equation 68. Therefore, the pair creation begins from early time to approach minus infinity, where the Ricci scalar curvature is given by R equal to h squared of tau, and induced energy momentum tensor of created particle is negligible compared to the Planck mass, and finish at the late time to approach 0, where the Ricci scalar curvature approaches 0, and the induced energy momentum tensor of created particle are given by equation T00 and T11. Therefore, in this picture, the time scale of pair creation is of order Hubble time, and variation of Ricci scalar curvature and trace of induced energy momentum tensor are given by, then the variation both of sides of equation 67 yields to the evolution equation for Hubble parameter as equation 70. Therefore, if T is larger than 0, the Hubble constant decays. This condition holds for the case of heavy Dirac field created by an electric field background with the strength lambda is smaller than lambda star, whereas Hubble constant amplify and super acceleration phenomenon with h dot is larger than 0 occur in the condition that t is smaller than 0. This is the case for the light Dirac field created by unbounded electric field strength or creation of heavy quanta in an electric field with strength lambda is larger than lambda star. Further work, besides I have computed the mass fermionic current in three-dimensional de Sitter spacetime, and these results are ready to be submitted. Adiabatic regularization for a scalar field has been studied and developed, but compared to the scalar field, the study and development of this method to improve the physical quantity made of fermion field are new. In this work, the back reaction effect of trace of induced energy momentum tensor on the gravitational field background was studied by using of Einstein field equation. But as we know, there is no Einstein gravity in two-dimensional space-time. Therefore, I want to obtain real cosmological conclusion by examining the back reaction effect of trace of energy momentum tensor in four-dimensional de Sitter spacetime and by using Einstein field equation.
Thank you, Mina. Thank you for the nice talk. Any questions from the audience? Paul?
I have a couple of questions. So thank you, Manizheh, for that talk. A lot of interesting details there. How difficult would it be to generalize your results to 4 space-time dimensions? 4-dimensional de Sitter space. Would that be possible? Do you understand?
The current for fermion in four-dimensional de Sitter space-time has been calculated by in a reference to I think this method has been worked in four-dimensional de Sitter space-time, and although the calculation, the computational calculation is higher than with respect to two-dimensional de Sitter space-time.
And I have another question. What happens in the massless limit when the mass goes to 0? Does something horrible happen with the stress tensor?
For massless, I have been calculated this problem for massless, and I have not obtained the finite result yet.
Right, I would expect it to diverge, that's right. And I have a third question, and then I will be quiet. If you apply your method to two-dimensional space-time, but not de Sitter space, but like a black hole, a two-dimensional black hole, what happens to the Hawking effect? Have you thought about that problem?
I have not investigated this problem, and I don't know which conclusion obtain for this problem, but it is the a very interesting problem to solve.
Right. I would, if you solve it, I would like to know the answer. Thank you.
Thanks, Paul. Any other questions? If no, let's thank Mina again. Thank you.
Welcome.
Thank you.
And let me just say how pleased we are that you have been able to give your lecture today. And I'm sorry it's so late where you are, but thank you for sharing your insights into this important problem. And we look forward to seeing you in the future. So goodbye and good night.
My pleasure. Goodbye.
Thank you. Bye.
Thank you.